Okay, so in this video, I'm going to briefly talk about the outline of procedures for groups 4 and 5 cations, the last two groups in our qualitative analysis scheme. So as you can see, our group 4 and 5 cations are at the top: barium, calcium, magnesium ions, sodium, potassium, ammonium ions. And so this is both group 4 and 5. So group 4 is the insoluble carbonates. So I circled those in purple. So those are the insoluble carbonates. So barium, calcium, and magnesium all form precipitates with carbonate anion. Group 5 are the soluble substances, right? Soluble ions. Ammonium, potassium, sodium ions do not form precipitates with most things. They're very, very soluble. Okay, so we'll go ahead and start with looking at separation of the group 4 and 5. So our first two steps, first, our substance is quite acidic or basic, excuse me, when we get it. So we have to add some hydrochloric acid. But then step 2 is we want to make it basic. So we want to make it basic and just basic. So not too high of a pH, but just basic enough, so we can precipitate out the carbonates. So I want to talk about this step a little bit more because it actually reviews some of the material we covered in Unit 2. So step 2, right, we need the solution to be slightly basic for the carbonate precipitates to form. So let's think about this. Let's talk this through. So let's just look at magnesium carbonate. The same thing would apply for the other two, barium and calcium carbonates. So I'm writing my KSP expression, which means solid on the left, ions on the right. So this is my KSP expression. All right, and so what are the things that affects the solubility of our substance? Like we went through this in Unit 2. So there were 4 things that affect the solubility of an ionic solid. So the 4 things to remind you are pH, temperature, common ion, and the formation of a complex ion. So what factors affect solubility? This is in your notes from Unit 2. The first one is pH. The second one is temperature. The next one is common ion, so at the common ion effect. And the last one is the formation of a complex ion. So we went through all of these in Unit 2. So what I'm talking about here in step 2 is we need to make this slightly basic for a carbonate precipitate to form. Okay, so which effect are we talking about here? Well, we are talking about pH, right? So we're talking about pH affecting the solubility of this magnesium carbonate or whatever ionic solid we're talking about. Okay, well, how is it affected? So pH affects the solubility of solids that contain an anion from a weak acid. So again, this is review from Unit 2. Okay, so pH affects the solubility of solids that contain an anion from a weak acid. Well, do we have an anion? So I'm looking here at magnesium carbonate. So carbonates are anion. The weak acid is carbonic acid, right? Or the acid that forms is carbonic. It's a weak acid. So carbonate is an anion from a weak acid. So the pH is going to affect the solubility. How does that work? Well, here's a reaction, right? If I have hydronium, so I have some acid in there, and I have carbonate, it is going to react. I have a single arrow because I'm talking about hydronium here, forming some carbon or HCO3 minus and water, right? So we have to go back to our original reaction to think about what's happening, right? So 2 things are going on. If I have magnesium carbonate and I add an acid to it, this reaction is happening. So I'm removing some of the carbonate, right? So in an acidic solution, right, the carbonate is going to decrease in an acidic solution. Okay, so this is an acidic when I have hydronium. If the carbonate decreases, right, that means the reaction is going to shift right to reform that carbonate ion, right? Le Chatelier's principle, we remove this, we decrease the concentration, the reaction's got to shift right to replace it. So what would happen to the solid? Well, the solid would dissolve. Okay, so that's why we don't want an acidic pH when we form this. If we have an acidic pH when we form this precipitate, some of it's gonna dissolve, right? We want to precipitate all the magnesium and with the carbonate. So that's why we want a slightly basic pH. Okay, so that's gonna allow for the precipitation of magnesium carbonate and not dissolve that solid as discussed if we have an acidic pH. So other ions, right, anions affected by the pH, here's just a few examples, and these you might see in this lab, are chromate, oxalate, and phosphate, right? So those also are affected. If we have a solid that contains one of those anions, the pH affects it in the same way we talked about here, right? If it's acidic, it's going to react with that ion, it's going to remove some of it from solution, and we can dissolve the solid. Okay, so a lot of these qualitative analysis use all the concepts we've been talking about all semester, right? So you can't just, again, it's a cumulative class, right? Chemistry is cumulative, so we can't forget things even from Chem 1A, right? That go into our qualitative analysis schemes and other things we talk about. Okay, so going back to our flow chart, so that we talked about kind of step 1 and step 2. So at the right pH, a slightly basic pH, we get our precipitates of barium, carbonate, magnesium. All right, and so that's going to actually be a white precipitate. So it's going to be a white precipitate. Okay, that looks a little bit something like this. But now we want to, make sure we can see, well, do we have, because right here, all 3 of them precipitate. So we got to separate further. All right, so our next step, right, would to be add a weak acid. Well, making the pH acidic dissolves the precipitate like we just talked about, right? It dissolves carbonate precipitates. So then we get these ions in solution, and now we can further separate them. We can add potassium chromate, and in this case, right, so following here, potassium chromate will precipitate out just barium, and it gives you a yellow precipitate. So here's our yellow precipitate of our barium chromate. Okay, so yellow precipitate. If we add HCl, it will dissolve our barium sulfate to give us barium ions. Just a double check. So this is just a double check to make sure it's barium and not something else. Then we can add sulfuric acid, and that will give us our barium sulfate precipitate. Okay, so what that looks like is that's a white precipitate. Okay, so we kind of had 2 conformations here to make sure it's barium. Getting this yellow precipitate at this step, dissolving it in acid, so the chromate is removed from solution by adding the acid as discussed. And then we get the barium, and adding sulfuric acid, then we get the barium sulfate white precipitate. All right, so looking at the other side of the flow chart, the calcium and magnesium is in solution. All right, so at that case, we can then separate our calcium and our magnesium by adding oxalate in a basic solution. So again, similar theory to what we talked about, right? To make that, so we wanted a basic solution. So it's the same idea. We wanted a basic solution for adding carbonate. And in that case, we have a couple different tests for calcium. At this point here, we should get a white precipitate. So it's actually going to look very similar. So we have a white precipitate here. So kind of boring colors compared to our group 2 and group 3. And then we can dissolve it in acid. Again, that same idea that we talked about when we talked about the carbonate precipitates. And then we can do a flame test for calcium as well to just be doubly sure we have calcium present. And that's going to be a red-orange flame. So I posted some links to some videos where you can see some flame tests and what they look like. Okay. So at that point, then we should have had magnesium. So there's actually 2 tests for magnesium, because not all the magnesium will precipitate out. It's the most soluble of the carbonates. So you would actually only need 1 positive magnesium test, right? And you're actually going to test twice just to make sure, right? So as long as you get 1 positive test, right? So for magnesium, right, you just need 1 positive test. Right, so but you want to make sure you do it twice. So you might not get it, over here. So then you'd want to make sure you test the supernatant from step 2. So in this case, we would have magnesium in our supernatant. We would add sodium hydrogen phosphate and get a white precipitate. Again, it's going to look like this. But the main thing is dissolving that precipitate, and then making it basic and adding this magnesium reagent, which gives us what we call a blue lake. It's a really dark blue. Okay, so it's a really dark blue. You can't even really see it well here. This is the picture I had for it. It's some solid, and like the blue is absorbed into the solid. So it's what they call a blue lake. I don't know why, but it's really dark blue. Okay, that's what we're looking for. So again, if you got a negative here, you'd want to test the supernatant from step 2. And then if they're both negative, then no magnesium. One negative, one positive, magnesium is present. Okay, so last ones we need to talk about are the soluble ones: sodium, potassium, ammonium. All right, so step 2, what did we add? Ammonia and ammonium carbonate. So even if there was no ammonium up here, we're going to have ammonium at this point. We add it. Do you guys see that right here? We add ammonium. So we're actually not testing for ammonium at this point. That's why down here it says original sample, right? Because if I test for ammonium here, of course I'm going to get a positive ammonium, right? We added it. It's step 2. You have to test for ammonium on the original sample. Okay, so original sample, you have to test for ammonium and also sodium, right? If this is especially the general unknown, you've added sodium a million times throughout group 1, group 2, group 3. You get to this point, if you're doing, the general unknown, which we're going to do next week or in a couple weeks, you're going to get a positive for sodium no matter what, right? So you got to test for sodium on the original sample. So here you actually could test for potassium. Okay, you can do the potassium twice here, but I'm going to talk about it down here. So we do sodium, potassium, ammonium on the original sample. It's very, very, very important. Okay, so our ammonium, what we do here is we add, so this is actually step 9, is we add sodium hydroxide and heat it. So you would actually do it, the best way to do it, and you actually did this in 1A if you took chemistry at Saddleback, is you'd have it in your little beaker, you have your solution down here, and the gas is going to turn your litmus paper. You have your litmus paper on like a little glass dish here, and your litmus paper goes from red to blue. So you have this red litmus paper here, and the gas has to turn it red to blue. So this is turning blue from the gas, not from the liquid, because the liquid is, of course, sodium hydroxide. So, of course, it would turn blue. So the gas has to turn this litmus paper blue, right? So you would actually do this in a beaker with a watch glass, as I described. So if the liquid splashes, right, onto the litmus paper, well, that could give you a false positive, right? It has to be the gas, right? It has to be this ammonia gas that is turning red litmus to blue. And again, it has to be the original sample. Okay, our sodium is a flame test, and it is a yellow or yellow-orange. Theoretically, it should be yellow. I'll post some videos. Sometimes it looks more orange. It's actually pretty tough. So, I'll be giving you data, so you're lucky. That's a hard one sometimes to do when we actually do the lab in person. So that's one benefit of quarantine here. So here we have a yellow or yellow-orange is flame for sodium. So that's what we're looking for. And we want to look for potassium through a cobalt glass. So again, Chem 1A here, you talked about this. So the yellow flame will mask the purple violet flame we are looking at for potassium. So you have to use a cobalt glass. So this is a piece of blue glass. You did it in Chem 1A at Saddleback. If you had Chem 1A somewhere else, you might not have done this. So here's my color wheel. So I'm going to put my colors, Roy G. Biv. So yellow, G, Biv, indigo, violet are on the same. So cobalt glass is blue, so that means it's transmitting blue light. So across from the color wheel is orange, so that means the orange is getting absorbed. Okay, and the cobalt glass is actually kind of a bluish violet. So it actually is also, so it's kind of both of these colors. So it's a mixture of like the blue, indigo, violet. So both yellow and orange are being absorbed. So the cobalt glass absorbs the yellow-orange light from the sodium ion that is also could be present, right? So maybe in your unknown, you might not even see that yellow-orange light. You would just see the purple, which means sodium would be absent. If you see the yellow-orange light, you would look at it through a cobalt glass, and you would see the purple or violet light for potassium. Okay, so that's what you're looking for. You got to do the cobalt glass. And so you have your purple violet color, again, either through cobalt glass if sodium's present. If there's no sodium, then you wouldn't, you would see it without the glass. So I said that the potassium and sodium ion and ammonium ion are soluble. Well, there is one compound, this tetraphenyl borate, or I think that's what there's 4 phenols, boron, with the boron, and that actually will form a white precipitate with potassium. So that's another test, just, you know, if it's sometimes hard to see those flame tests. So that would be another test for your potassium. Okay, so go ahead and watch videos on the flame tests, and I will be posting a discussion question for you to think about for qualitative analysis, and then you will get your unknown data soon.